Alright guys, this is the question from the last week's discussion. This is the Monty Hall game, and we're looking at the probability we win if we switch and the probability we win if we don't switch if we play the game 5 times. So it's a probability distribution where our random variable x is discrete, but it's also binomial because we can either win or not win. Alright, the probability we win is always going to stay the same each time, except for when we go over from switching to not switching. But for each time we switch, it's always going to be a 2/3 chance we win. Each time we don't switch, there's that 1/3 chance we win. So because this is binomial, we can use binomial PDF to find each of these probabilities. For instance, I could plug in for the first one, and make sure you're not picking normal PDF and normal CDF. I could pick off the binomial PDF. Right, we're playing 5 times, so that's n. The probability we win, the probability of success if we switch, was 2 out of 3, so 2/3. And then if I wanted to win 0 times, I'd plug in a 0 here. So there's the binomial PDF for 0, so I put a 0.004 there. Right? And then if I wanted to do it for 1, I could hit second enter and change that 0 to a 1. Alright, and then 0.041, second enter, change that 1 to a 2, and so on and so on and so on until I got to 5. Alright, but I was reading something in the table. One of you mentioned a method to do this. There's actually a very quick way to do this with your calculator. So what I'm going to show you is, if you go into your stat menu, your stat editor, so we get there by pressing stat, alright, and then edit, go to your editor, and then in list 1, come over here and just put in those x values. So we can have 0, a 1, a 2, a 3, a 4, and a 5. Okay, and then once we've got our possible values of x, we hit second mode to get back to the home screen. And I'm going to start just like I was doing that very first probability. I'm going to go into the distribution menu, second vars. I'm going to find binomial PDF, and I'm going to tell it we did 5 trials. The probability we win is 2 out of 3. Right, but instead of telling it 0 and then going back in 1 and then going back and changing to 2, I'm going to tell it where the list is of all these values. The list is under list 1. Notice that's the second function of the 1 key, so I press second 1, and now it's going to put in every value from list 1 at a time into the binomial PDF with 5 and 2/3 as n and p respectively. Alright, and then I'm going to close that off, and then in addition to that, I could hit enter here and get the probabilities, but I'm also going to use the store feature and tell it to store those probabilities into list 2. Alright, and now when I hit enter, it says the probabilities, but if I hit stat and enter to go back to the editor, list 2 is now the probabilities that I'm looking for here. Okay, so I get all the probabilities from 0 up to 5. Now I hit second mode to go back to the main menu. I can hit second enter, bring back the last thing I just did, and now I can change that from 5 2/3 in list 1 to 5 1/3. And now I'm switching over and I'm doing the probability table for not switching. Alright, hit enter, hit stat, go over to this, and go to editor, and then there is our probability table for not switching. So it looks like this when we do it: 0.04, 0.041, once it's just filling in the table. And then notice this is the inverse of that, meaning that the value for 5 is now the value for 0 here. The value for 4 is the value for 1. The value for 3 is the value for 2, etc. So it's inverted completely. And this is just a reminder where everything is. This list 1 in yellow is second 1. That little arrow is the store button, right? And then list 2 is second list 2. Okay, and I did the same thing over here, just changed the 2/3 to a 1/3. Alright, and then the questions ask, what do you notice about the values? Why do you think this is happening? Alright, what do you notice about the values? What do you think? Why do you think this is happening? The distribution for the probabilities for 0 through 5 is completely reversed when we go from one table to the other. Okay, meaning that these probabilities here are increasing from 0.04 to 0.329, and then it mirrors, and then it decreases. Well, these start, or this one's ended, It peaks to 3.29, and then it goes back down with the same values that this rose from. Alright, so again, this is just showing the probability of 0 given that we switched is equal to the probability of 5 given we did not switch. The probability of 1 given we switched is equal to the probability of 4 given we did not switch. And so on and so on and so on. The probability of 2 switched is equal to the probability of 3 did not switch, and etc. Alright, why is this happening? There's three main reasons. Number one, the probability of winning when switching is equal to the probability of not winning when not switching. Right? Well, what does that also tell? Well, because this is binomial, it tells us the probability of not winning, the complement of this, when we switch, must also equal the complement of this. Right? The probability of winning when we don't switch. Alright, and then overall, what does that say? And then the big gist of it, the values of P and Q from switching are the same values for Q and P when not switching. So all we've done is just switched what we're calling P and Q from one to the other. Okay, that's the first reason that it's happening. All right, the second reason it's happening is that NCX is equal to NC n minus X, meaning the number of ways that I can choose X successes out of n is also equal to the number of ways I can choose n minus X failures out of n. Right, and it would have to be that way. Meaning that if X is 3 here and n is 5, the number of ways I can win 3 times has to be equal to the number of ways I can lose 5 minus 3 2 times. Alright, and I can show you with the formula that this is true. Alright, so here's the formula for NCX. Alright, n factorial over the top, and then remember we subtract these two, n minus x, right, and then put a factorial after that, and then just whatever this is, that's what we also have factorial of on the bottom. So here, just think about it for a second. N is out in front still, so that means I'm still using n factorial for the numerator. Alright, where did this piece come from? It came from subtracting these two. So if I subtract these two, I get n minus parentheses n minus x bracket factorial. Alright, and then remember this piece was the last piece that gets factorial on the bottom, so put a parentheses n minus x, alright, parentheses factorial. Alright, now think about it for a second. How does this work on the bottom? I'm going to distribute that negative sign through. Right? This negative sign goes through here. I'll get n minus n. Right, and subtracting a negative is the same thing as plus x factorial. And then there's still that n minus x factorial. Right, and then the n's cancel because n minus n is 0. 0 plus x is x. So that becomes x factorial. Well, if you look at that denominator that's left here, this denominator, x factorial times n minus x factorial, is the same thing as this one. Right, because the commutative property, if I multiply x factorial times n minus x factorial, I'm going to get the same thing as if I multiply n minus x factorial times x factorial. Alright, 3 times 4 is 12, 4 times 3 is 12. So these two things are the same. The denominators, the numerators are obviously the same. So what does that tell me? That tells me that this is equal to NCX. So what have we just shown? We've shown NC n minus x is equal to NCX. Okay, so they're the same thing. Now, that's the second thing. The last thing that lets us know that these two are the reason why we're seeing those two types of tables, those changing values in the tables, is that multiplication is commutative. Right? Commutative means a times b equals b times a. Alright, 3 times 4 equals 12, 4 times 3 equals 12. So these are two different scenarios that could happen. All right, this is the probability that I win 3 times if I switch. All right, and because it's possible to win 3 times, we can compute that probability. So here's how we would compute it by hand. Well, this is also a possible probability if we didn't switch and we win 2 times. Alright, well, if you look at it, if you take the time and look at it, we just said that 5C3 equals 5C2. How do I know that? Because these last two numbers add up to 5. Right? 5C3 is the same thing as 5C2. Check it out on your calculator to verify it if you need to. Alright, we just showed it on the last slide, but 5 math, choose 3, and then 5 math, choose 2. Right, they're the same thing. So no matter what, if these two last numbers add to n, then those two combinations are going to be equal. And then because multiplication is commutative, there's 2/3 to the third power, there's 2/3 to the third power, there's 1/3 to the second power, there's 1/3 to the second power. We can multiply in any order we want to. So what does that tell me about these two things? They're equal. Okay, so because the commutative property, because these things are just going to flip around from one to the other, the order that they show up doesn't matter. So they can flip around all they want to. When we're multiplying, we can rearrange it how we want. So the commutative property of multiplication is the last and final thing, along with the fact that these two values that are complements show up from one to the other. There's only two values of p and q here. They're just changing who is who. And then the fact that 5 choose x is equal to 5 choose 5 minus x for these. Alright, those are the three things that are allowing us to see what we're seeing in these tables, meaning that these values show up, but they just show up in the reverse order over here.